Hello and welcome to Chapter 11. So Chapter 11 is one of the longer chapters, forms the foundation for a lot of things in the future. So we'll take a little bit of extra time, make sure it's super solid on this. And for this video, I'm going to call this Cliff Notes. So we'll go through the bare bones, really basic ideas of what you're getting through. And as you work through the quizzes and homeworks, you'll iron out a lot more of the details involved in this. What we're talking about here, kinematics of particles. So let's define some terms. Kinematics is analyzing motion with calculus. So we're going to look at position to velocity to acceleration, and I think you've done a little bit of this in physics before. So acceleration is dv dt, and velocity is dx dt. And this is where actually birthplace of calculus. So Sir Isaac Newton was one of the fathers of calculus, and it was looking through these kinematic relationships that kind of came about. And particles, so the first half of the book could be concerned with objects that are not rotating. So objects that don't rotate, each piece of that object has the same velocity, has the same acceleration, versus the last half of the book will look at objects that are rotating, in which case different parts of that object have different velocities and accelerations, and we'll keep track of like the center of mass and how everything rotates or moves around the center of mass. So we'll start with just the simpler kind of motion, non-rotating objects. And the very simplest motion, of course, would be one-dimensional linear motion. So just a particle going back and forth in a straight line or straight up and down. Once we figure out one particle, changing velocities, changing accelerations in one dimension, we'll then look at two particles. So things like, when are the cars going to crash, or when is a ball going to hit an elevator floor, where you look at one object and another object and then you compare how they're moving relative to one another. Once we're set in one dimension, we'll enter the second dimension and look at curvilinear motion. So this is where something, instead of just traveling in the x direction or the y direction, it's going to have x and y components, and that's generally describing a curve. So that's why it's called curvilinear motion. It's going to be similar to what we did in statics, where you start breaking forces into x and y components. So we will break velocities into x and y components and accelerations into x and y components, and really get into the vector nature of motion. Looking at linear motion, so we're talking about distances and things like meters, velocity, meters per second, acceleration, meters per second squared. So linear motion versus rotational motion. And a lot of times rotational motion is going to be better to describe in terms of radians. So you're looking at how many degrees or radians something has rotated through. And instead of meters per second, we're looking at radial velocity, which is radians per second. Instead of linear acceleration, we'll have an angular acceleration, radians per second squared, and there's a lot of similarities between these two. So once you're comfortable in the linear realm, walking over to the rotational realm isn't too much, and you can see A kind of looks like alpha, V is kind of, omega is two V's smushed together. Sometimes just getting used to the symbols that are used for everything takes some getting used to. So you might want to get some scratch paper out and just kind of make a dictionary of terms for yourself, so that when you see these on here, you know that, oh, alpha, that we're talking about radians per second squared, that's our angular acceleration. Okay, last thing, we're going to be looking at some different coordinate systems. I think everybody is used to using x in the horizontal direction, y in the vertical direction, and x, y, z. Sometimes we'll reorient that coordinate to be normal and tangent to a surface just to make the problem easier to solve. For rotational motion, whether that radius is constant or not, we'll be looking at radial and transverse directions. And these really aren't that different from one another. You can call x and y, or PQ, or LM. I mean, you can call that anything you want. and these are just slightly more descriptive names that describe how we're rotating that coordinate system. But if you can break things into x and y components, it's the same idea to break it into normal and tangential components. So if you just get used to those new names, these will actually make a lot of problems easier to solve in the end. One-dimensional rectilinear motion. This is where we have some object and it's traveling either straight back and forth in the horizontal direction, or maybe it's a ball getting thrown straight up in the air and falling straight back down. So everything is happening along a single line. And the graphs we're going to analyze with this, you've probably seen these before: position, velocity, and acceleration. And I want you to really pay attention to the relationships between these three graphs. Graphs in dynamics are similar to free body diagrams in statics. So when you go through a free body diagram to visualize the forces and what's happening in a system, when you think about how something is moving and to visualize how the velocity is changing, how the acceleration is changing, and to really understand the motion and how that's progressing, that's where these graphs come from. So looking at these graphs and studying them so that you can picture the motion that these graphs are describing is really important. The strange thing about these graphs, so position versus time, if you think about this, time is a very different physical quantity than position is. So position you measure with a ruler, meters, miles, feet, versus time, you're looking at a clock here. Time is a very different thing than position, and trying to get those two things into your mind and on the same graph, it takes a little bit of thinking through it. So position of this blue line, what it's describing is an object that starts at 0. It goes straight up to 32. So remember, linear motion, straight up. There's no horizontal motion at all going on here. And then it kind of hangs out right here. It's going to turn around and then come straight back down. So it comes straight back down. And then we're looking at what time each of those positions happened at. Velocity to position. So velocity is something like miles per hour, miles divided by hour, meters per second. It's some kind of a distance divided by some kind of a time. And what that is the slope of our position curve. So how does the slope start out? It looks like the slope is pretty flat coming in. So 0 slope, 0 velocity. But then we start getting steeper and steeper in here. See how the slope is getting steeper? Our velocity is getting larger. And right here it looks like that's the steepest that our slope gets, is right here. And then it starts getting shallower. Right up here at the top, the slope is 0, right? 0 slope at the top, 0 velocity. This whole side is positive. So positive, positive, positive. We're speeding up, we're slowing down. So the slope is getting steeper and the slope is getting shallower to 0. And right here is the turnaround point. So we're going from a positive slope to stopping, turning around, and now we have a negative slope. So a negative slope on this other side. Slope of position is velocity. The slope of velocity is acceleration. So you can see we start out with a positive slope again, but that slope, what's happening to it? So it's getting shallower and shallower up to the top where it's flat on the top. So again, the slope is 0. That's where our acceleration is 0. Usually the interesting parts in problems are maxes and mins and turnaround points, what's the highest something got to. So we're really looking for where the slope goes to 0. If I want to find the tallest position, the easiest way to do that, and I have to figure out what time that happens at. If I can plug that time in, I can figure out where the position is. And I'll do that not from the position curve, but from the velocity curve. So it's really easy to set velocity equal to 0, solve for the time velocity equals 0, and then when I figure out what time that is, I can take it back to our position curve and plug it in. So really think about how the slope is changing and how you can use these 0 slopes to find maxes and mins and turnaround points and the tallest point. And so you really go back and forth between these graphs. So if I want the max velocity, I'm going to pop down here, look at where acceleration is 0. That'll help me get the time where that turnaround point is. So you really go back and forth between these graphs to figure out what's happening. Okay, so let's walk through just a little bit of the calculus. The slope on the position versus time curve is velocity. So dx dt, dy dt, or for arc length, we'll say ds dt. So some kind of a length over some kind of a time. And take these graphs one piece at a time. So just watch how that slope is changing to think about how velocity is changing. And then to go from velocity to acceleration, so the slope of that velocity curve, that describes our acceleration. The best way to think of acceleration is the unbalanced forces acting on the system, F equals ma. So if the forces don't add to 0 like statics, whatever doesn't balance, that's which way it's moving. If I have a positive acceleration, it's like there's a positive force that's pushing on it, or a negative force that's pushing on it. Or an acceleration of 0, that is describing an equilibrium system where the forces actually add to 0. So where acceleration is 0, that's describing a statics problem. Okay, so a equals dv dt, b equals dx dt, and this case is something where our acceleration is not constant. So what if we have acceleration created by a motor, or I don't know, it's not 9.81 though, it's not just a number. It's some kind of a line and the acceleration is changing with time. How do we deal with that? Let's start with a position equation. So we have position as a function of time, and this could be any kind of an equation. So x equals x naught plus vt plus 1/2 at squared if acceleration was constant. And in this case, we don't have a constant acceleration, so there's this different equation that describes the position of an object as a function of time. If we know position as a function of time, how would we get velocity and acceleration? Well, we just crank through some calculus, right? So if we know that v is dx dt, then we'll take the derivative with respect to time, and we can very easily go from position to velocity. Same thing from velocity to acceleration. So we know acceleration is dv dt, so just take another derivative, and we have our acceleration. How about going the other direction? So let's say we start with knowing our acceleration and what that's doing. How would we then go backwards and get velocity? Let's go ahead and rearrange this equation. So if we have acceleration as a function of time, I'm going to move time over here, so a dt equals dv, and we can then integrate that, where instead of just a in here, we're going to substitute that for an entire equation. Okay, so instead of a dt, we're going to put this equation in here, integrate with respect to time, and that will get our velocity. So the area under our curve, now we've transitioned from the slopes of lines like dx dt, dv dt, to the area under a curve. So that's what we're doing when we're integrating. Area under the acceleration curve, a dt, is going to tell us how our velocity is changing. And a lot of times for these ones you'll need to know some boundary conditions, but you can go from acceleration up to velocity, and then from velocity, v equals dx dt, we're going to do the same thing. So I'm just going to take this dt, move it over, because we have velocity as a function of time. So I'm going to take this whole equation and we're going to integrate that equation with respect to time. Okay, so the area underneath the velocity curve is then going to be our change in position. Area under velocity curve, change in position. So we're just chugging that entire equation in here, and we can crank through it, and now we have our position. So whether you're going from position to acceleration or acceleration up to position one way or another, it's just calculus. If you have an equation for one of these three graphs, you can figure out what the other graphs are too. Let's try out a different scenario. What if we had an equation, but instead of something as a function of time, we had, let's say, acceleration as a function of position instead. So this could be like a spring, F equals ma equals kx, where acceleration is going to change with position. So we can do some graphs in that case as well, but instead of time, we have position then on that axis. So acceleration as a function of position. How could we get velocity information or position with time information if this is where we start? There's a couple little tricks that we can do. Here is one of them. So acceleration equals dv dt. How can we get rid of that dt and replace it instead with a x? Because now we're interested in things changing with position. We're going to use a little chain rule here, just multiplying it by 1, dx over dx. And this dx over dt, what that is, that's our velocity. So this goes ahead and gets rid of that time dependency, and now we have acceleration not as a function of time, but acceleration as a function of velocity and position. So that's kind of a neat little trick there. Let's go ahead and rearrange this equation. So we're going to bring this dx over. We're just grouping everything that has an x in it because now our equation is a function of x, and we'll walk through the same kind of calculus stuff. So if you integrate this, now we can go ahead and get some velocity information, whereas before we only had acceleration information. So here we go. We're going to plug that whole equation in here. Acceleration dx equals v dv, and go ahead and integrate that, and now we have a relationship between velocity and position for this system. So we're going from acceleration to velocity, and the difference is we're dealing in positions instead of times now. Okay, what can we do with this? Well, what equations do we have for velocity? We know velocity is dx dt, so we can rearrange this again, only now there's no times in here, right? So if we're going to combine like terms, it's going to start getting a little bit messy because we have velocity in the denominator now. So some of this, the calculus can get a little bit messy, but you get the point. You can rearrange these however you want, and depending on what relationships you are given, you can walk through and get other relationships. And it's kind of neat because the mathematical manipulations that you do here actually do correspond to how acceleration, velocities, and positions relate to one another. Okay, so as a function of position instead of as a function of time. Here's one scenario. This is the first one we did, what everybody is used to, a equals dv dt. If we have acceleration as a function of position, then we use that little chain rule. We get v dv equals a dx, and we can integrate with respect to position instead of respect to time. There's one more scenario out there, and that's say we have acceleration as a function of velocity. So this would be a situation like drag is usually a function of velocity. And once again, we can kind of manipulate this thing. So dv dt, we can combine all of the velocity terms in this one, or if we were interested in a position relationship, we can chug in this v dv equals av. So these ones tend to be a little bit messier to integrate, but what you do is you just look at your problem statement, what quantities do you need to relate to one another, and you can pick off of this chart whichever relationship you need and crank through the calculus on it. Constant acceleration, hopefully you've seen this before in physics. So here we have acceleration equals 9.81 meters per second squared, or 32.2 feet per second squared. So it's just a number. It's no longer an equation, just a number, some constant. And in that case, when we crank through these relationships, okay, so now instead of an equation in here, we just have like 9.81 or something. So that makes the calculus pretty easy, and we get equations like acceleration times time is change in velocity. V equals V naught plus AT. Have you seen these before? Hopefully this starts ringing a bell. This is a good constant acceleration. Now remember that these equations can only be used if acceleration is constant. So it's a whole different ballpark if there's something changing here, if there's some equation that we have to crank through. What's our next step? So V equals dx dt. We can crank through that calculus. We just figured out velocity is also related to acceleration, so let's plug that in here. And what does this turn into? So we have VT, 1/2 AT squared. Hopefully you've seen this equation before too. So position as a function of time for a constant acceleration is our classic x naught, so that the starting position, the starting velocity, that's what those little sub-knots are. So this is where we start, and then the finishing position. So time progresses with this constant acceleration the whole way through, and at the end of it we're at this new position from where we started from. Last but not least, so let's use this other relationship where acceleration is a function of position instead of time. So acceleration is v dv dx. And in this case, so I'm just going to bring that dx over here, a dx equals v dv. And this is where, if you don't have any interest in what's happening with time, you're just interested in the relationship between velocity, acceleration, and position, then this is what you go. And these three equations, all three of them apply to any situation that's constant acceleration. It's just sometimes one is easier to use than another. So if you don't care what the position is, just use this one. Or if you don't care what the time is, then just use this one. If you have to relate all of it, then you're stuck with a quadratic formula or something. Okay, so constant acceleration equations. Remember how these things are derived, and remember they only work if acceleration is constant. Relative independent motion, what are we talking about here? Relative motion, so car A relative to car B. Usually when we measure how fast something is going, it's relative to the ground. And so you kind of have to teach yourself to ignore the ground and look at something relative to a different object instead. Independent versus dependent. So what A is doing, let's pretend like her eyes are closed and she has no clue what B is doing, off in her own independent world. So there's no strings between them. There's nothing that B is doing that can change what A is doing. It's completely independent, or like this ball. You throw the ball up in the air and it's off in its own little world doing its own independent thing, versus the elevator is off doing a whole different independent thing. And it's not until they crash into each other that they see one another. So independent motion. And to solve these things, what we're going to do is just look at one of the objects, see if you can figure out all the equations for one object, and then ignore the first object and just look at the second object. Figure out all the equations for the second one, and then we're going to compare their positions, compare their velocities, compare their acceleration. So where does the position of A equal the position of B, sort of a thing. Okay, so here's an equation. The position of B relative to A, and this is how it's going to write it, so kind of remember the order of this. So when you see x, B slash A, that is B with respect to A, and what that means is if you are the one sitting in car A, So you are in A, it's with respect to you and what you see everything else doing. So from A's perspective, what is happening in the scenario? So we have B is traveling to the left, negative 40 miles per hour. A is traveling to the right, positive 65 miles per hour. So this is relative to the street, but what is it relative to one another? So let's say the lights are out, it's dark, you can't see the street, all you can see is a pair of headlights heading towards you. How fast does it look like those headlights are traveling? Well, it's not just 40, because you're both traveling, it's 40 plus 65. So those headlights are approaching you at 105 miles per hour. And it looks like they're traveling to the left. So if we plug that into this equation here, so we have, I guess that would be velocities, not positions, huh? So here's the velocity equation. Okay, so we have a velocity of B is negative 40, and then we subtract off the velocity of A, so we have negative 40 minus 65, so we have negative 105 miles per hour. So the velocity of B with respect to A, if you're sitting in car A, it looks like B is heading at you at 105 miles an hour. Okay, so there's relative velocities. You can do the same with positions and accelerations. And this is a one-dimensional example. Okay, so everything is in the x direction. When you see these equations, remember that we're not talking about just a scalar quantity here. These are all vectors. So we could split these up into Vx, Vy, just like force in the x direction or force in the y direction. And in which case, this is, how you add vectors together, head to tail, or break everything into x and y components and add everything in the x direction. So it's not just like 3 plus 5 equals 8 or something. These are vectors, and you have to add them as vectors. So let's go ahead and look at an example where you have two cars, and this time we have things going in two different directions, so we're going to really realize the vector quantity of this thing. Okay, automobile A is traveling east, constant speed. As it crosses the intersection, B starts from rest. So B is waiting up here at 35 meters and starts from rest and starts traveling south with a constant acceleration of 1.2 meters per second squared. Okay, so you have the picture. So here's A, constant velocity, 36 kilometers per hour. And as soon as A is in the intersection, B starts moving. So starts from rest and then starts accelerating downwards. And what we want to figure out, determine the position, velocity, and acceleration of B relative to A. So here's that relative motion. So it's not relative to the street, it's B relative to A, 5 seconds after A crosses the intersection. Okay, so good practice when solving problems. First, just sit down and write down everything that you're given in this. In our old class, we had E2 paper, and there was a very strict format in how we had to present all of our homework, and it started by writing down what you're given. Sometimes if you don't know where to start, this is kind of the recipe for any problem. Write down what you're given, and that's where you want to start. So start with what you know and then work towards everything that you don't know in there. In this one, it's kind of like free body diagram of A, and that's the nice, you can define your system however you want. So ignore the rest of the world and just zoom in on one piece of it and figure out everything going on with that one piece. And then you're going to ignore the first piece and look at another part of it. So zoom in on B and just write everything you know about B. So take this one bite at a time, one chunk at a time, and that's, engineering principles of how you solve a good engineering problem, just one piece at a time. And that's how you get through this stuff. Okay, so what do we know about A? Well, we know the velocity. Make sure we've got the right units on here. Meters per second, that's kind of the standard unit that everyone uses, because 9.81 meters per second squared. So we have constant velocity, so acceleration of A is 0. That makes things easy. So velocity of A, it's constant. It starts at 10 meters per second. It ends at 10 meters per second, just constant velocity. So if you look at the position versus time, x equals x naught plus vt, 1/2 at squared. We don't have a in here, so it's just x plus vt. So just a generic position, and you can look at the units on this. So velocity is length over time times time equals length. So we know we have a good equation for our position. So here we've got equations for what A is doing, and we want to know what is happening at 5 seconds. So let's go ahead and plug 5 seconds into this problem. So 10 times 5, we're at a position of 50 meters. And our velocity hasn't changed. So now we know everything that we need to know about A. And we're also keeping track of direction. So this is a vector. A is traveling in the x direction, so we can write 10I or 10x, or I like to just write an arrow next to it so that we remember what direction that guy is going in. So here's the position, 50 meters east. Velocity is 10 meters per second east. Do the same thing with B now. Okay, so here's B. What were we given about B? He's accelerating down 1.2 meters per second squared. So that means his velocity is changing. Okay, velocity starts from 0, starts from rest, and then as soon as A crosses the intersection, starts accelerating down. So V equals V naught plus AT. It is a constant acceleration, so really key in on some of those words in a problem statement where you see constant acceleration, you say, yay, I can get out my constant acceleration equations there. And here is my position then. X equals x naught plus vt plus 1/2 at squared, or in this case it's the y direction. Okay, so we're going to plug in starting position, starting velocity, starting acceleration, and then at 5 seconds we just plug in 5 seconds for time, and we can see what his position is. Okay, so here's all the information for B. We're accelerating downwards, we have a velocity going downwards, we still haven't crossed the intersection, so we've gone from 35 meters to 20 meters. We're still 20 meters up north. Okay, now that we know everything that A is doing and B is doing, we're going to get out these relative motion equations and look at everything relative to one another. So, what is the motion of B relative to A, or the position of B? So remember, when you look at these, it's not x or y, this is the entire vector that we're adding together. And when you're adding vectors, you can either break everything up into x and y components, add everything in the x direction, everything in the y direction, or I like to actually draw a picture of those vectors and add them head to tail. So if we have XA, here's XA, 50 meters, so A is out here at 50 meters, so here's the vector for A. And we know that XA plus that B relative to A is going to give us the position of B. So 50 plus this relative is a 20. And it's a right triangle, so if you know two of the sides of that right triangle, you can figure out A squared plus B squared equals C squared. Tangent of 20 over 50 is equal to that angle. So remember your SOHCAHTOA, law signs, law codes. Just SOHCAHTOA. It's just a right triangle. But actually draw these vectors out and add them head to tail. So there's our 50, there's our relative motion, and you're adding vectors together here. Same thing with velocity. So what is our velocity of A? So A has a velocity of 10 meters per second east. So here's A is traveling over here. And we know that if we add our relative velocity onto that, we will get the velocity of B. So B has a velocity of 6 meters per second down. So again, I'm adding these vectors head to tail, and I know two sides of this triangle, so I can walk around and get the other side. So 6 squared plus 10 squared equals the relative velocity squared, and just tangent 6 over 10, that'll get us the angle for this thing. For acceleration, that's not too exciting. So because B is the only one that is accelerating, acceleration of A is 0, then B is what the relative acceleration is. It's down. And look at the direction of this thing. So B relative to A, So if you're in the car at A and you're looking back at B, this is the direction that you're going to be looking in. Velocity of B relative to A. So that's sometimes a little bit harder to realize. So A is going forward, but B is going down. And so the relative velocity is a combination of that forward and down motion. Okay, so if you can figure out what's going on with each car individually and remember everything with adding vectors together, you can figure out what relative motions are. So yeah, keep track of what's in the x direction, what's in the y direction, and get your statics book out if it's been a while since you've added vectors together. But these are all vectors. So anything to do with velocity or acceleration, those aren't scalar quantities, those are vectors. Independent versus dependent motion. So dependent motion, this is where objects are connected to one another with, I think most of the problems in this book, it's all strings. You could have magnetic forces or something like that too, but we'll just do pulley systems in this case. And these were done in statics too. I don't know if you remember back that far. So let's just run through one of those. The trick for dependent motion is, so think back, position, velocity, acceleration. If you can write an equation for one of those, you've got all of them. So first, let's see if we can just write an equation that relates the position of maybe this block A to the position of this block B, and know position turns into velocity, v equals dx dt. Okay, so we're interested in what positions and what quantities are changing with respect to time versus which quantities are constant. And if you think about what's constant in this system, the overall length of this cord is constant. So maybe this rope is 10 feet long or it's 50 feet long or something, but the overall length of that rope is some length, and that length doesn't change in time. Like how much of it is in this blue section versus how much is over here on the yellow side, that changes with time, but if you add it all together, that does not change with time. So we say I've got this little yellow chunk XA, and then I have two of these blue chunks. These two pieces they're changing together. That distance is changing. And if you add those together, it's going to be some constant value that's not changing with time. So if you can relate the positions of something, once you have position relationships, those position relationships turn into velocity relationships. And then one more derivative and you've got acceleration ratios. So position, velocity, acceleration. And if you're given information for what one block is doing, you can figure out what the other block is doing too. So maybe velocity of A is 10. If velocity of A is 10, then what does B have to do? Well, if they're going to add to 0, then 10 equals 2 times -5. So B would go in the opposite direction as A, and it would be going half as fast as A. So you can kind of think about acceleration or force ratios going on in that scenario as well. So that is dependent motion, and this is the trick. Just add up the length of the rope and then take derivatives and you've got the rest of it. Curvilinear motion. So in this case, we're going to have motion in the x direction and the y direction. Two-dimensional, so it's not just x, not just y. And everything you did with forces in statics, we're going to do with velocities. So if you have velocities, we can split that into x and y directions. SOHCAHTOA, right? So you have some angle. X is the cosine, that's the adjacent side, or y is over here, that's the opposite side, sine. So it's just a vector. Everything you did with vectors in statics and breaking forces into x and y components, we're going to do the same thing in dynamics, breaking velocities into x and y components. Let's go ahead and look at the x direction first. So this is one, just like statics. You look at everything happening in the x direction, then you look at everything in the y direction, then you put the two together. In the x direction, are there any forces in the x direction? I guess there could be air drag, but we're going to ignore that. So no forces in the x direction, no acceleration in the x direction, nothing to change the velocity. If there's a force, that would change velocity, but if there's no force and we have a constant velocity, and that velocity would be the cosine piece of that v naught. So there's the starting and the ending and the constant velocity for x. So if we plug this into our position equation, x equals x naught plus v naught t, we're not worrying about that acceleration, so we get this equation that shows what's happening in the x direction for everything. For the y direction, now the y direction, there is a force going on. We've got gravity, and so that's what we're going to plug in for our acceleration in the y direction. That means that our starting velocity in the y direction is going to be changing. So we start out with just that v naught sine theta, and that will change through the course of the problem. Gravity is going to be pulling down on it. So y equals y naught plus the starting y velocity, so that's that sine theta chunk of it, minus 1/2 gt squared. So there's our acceleration that's changing our velocity. So there's our position. We can plug in that v naught sine theta. We can also grab some other constant acceleration equations here. So v equals v naught minus gt. So there's how our velocity is changing. Here is an example problem. So we have something getting launched off of a hill, and we can set up our coordinate system. Usually just set the origin where the thing launches from. That makes sense to make all your measurements from the origin. And let's see what we're given. We're giving a starting velocity, so we can take that thing and break it up into x and y components. Starting position, so we're 150 meters up on that cliff, and we've got gravity acting in the y direction, and we're not going to worry about air drag or any forces in the x direction. Okay, so let's plug in our constant acceleration equations. In the y direction, in the vertical direction, that's going to be the sine theta chunk of that velocity opposite that 30 degrees over there. So we've got our starting velocity in the y direction, that's a stark green arrow, and we can just plug that guy right into our constant acceleration equations, plug in our gravity for acceleration, and voila, we have everything happening in the y direction. The x direction, no acceleration, so that simplifies things quite a lot, right? So the position, and we're measuring it just from the origin here, so position is just starting Vx times time, where that is going to be the cosine theta adjacent to that 30 degrees. So breaking that vector into x and y components and chugging through what's happening in the x and y direction. So what are the types of questions we can ask for this? How high does it get? Where does it land? What time does it land? We don't know the x position of where it lands. We do know that it's 150 meters off the ground. We know the y position of where it lands. So let's start with that. What equation relates the y position with time, right? So just good old constant acceleration equations. We know it's 150 meters down, starting position of 0. We know what our starting velocity is, 1/2 times gravity. So we can chug through this constant acceleration equation and figure out the only unknown we have in here is time. So get out quadratic formula and figure out what time it hits at. Okay, so here's the time. It's in the air for, wow, 20 seconds. That's pretty good. So once you have the time that it's in the air, we can then plug that into x. So let's say it starts at a position of 0. We know the x velocity, we know the time, we know we don't have any acceleration in the x direction, so now we know the x position of where the thing lands. And how high does it go? So this isn't a question with time. Let's go ahead and get out that v squared constant acceleration. So we know that at the highest point, what's the velocity at the highest point. So it goes up to the highest point, stops, and then it starts coming back down, right? That's why it is the highest point, that it's not going up anymore. Gravity has stopped it and is turning it around. So our velocity at the highest point goes to 0. We have our starting velocity, we have our acceleration. That'll give us how high it goes. So these constant acceleration equations come in very handy, and you can see how we're going back and forth between what's happening in the y direction and what's happening in the x direction. Rotational motion and different types of coordinate systems. Okay, so we've done x and y, horizontal, vertical. What if we have a system that is not in the horizontal direction? Then it makes sense to reorient our coordinate system, right? And if motion is happening in the x direction and there's no motion happening in the y direction, it makes sense to orient everything with the direction of motion, the direction of the forces. So by reorienting my coordinate system, I don't have to split friction or the normal force in x and y components. And just to be a little bit more descriptive, rather than calling this x and y, we'll call it normal to the surface of the normal direction and tangent. And it's the same thing, same way you break up forces in the x and y direction over here. That's the same thing you do over here with normal and tangent. We're just renaming it to indicate that we've reoriented it to line up with the surface over there. So in this case, if you have gravity and you're splitting gravity into how much is sliding down that ramp versus how much of the gravity force is held up by the normal force, that would be the only thing you have to split apart, because friction, it's completely in the tangent direction, normal, completely in the normal direction. So you can see it really does make it a lot easier to solve problems if you reorient your coordinate system with the system you're working with. Okay, so how does that translate into rotational motion? For rotational motion, it makes sense to put something kind of in this radial direction and then 90 degrees to it. And you can think of it as x and y, but once again we're going to just rename that into normal and tangent directions, or sometimes we'll call this a radial and transverse direction. So depending on whether our radius is constant or not, it's not tangent if the radius isn't constant, if you have some kind of a spiral. So the nice thing about this, velocity is always going to be in the tangent direction, versus acceleration is going to have two components. It'll have a component in the tangent direction and in that normal direction. Circular motion. So velocity instead of dx dt, dy dt. S is the symbol uses for arc length, and arc length is r d theta, d theta dt is omega. Let's just go through where this stuff is coming from a little bit. Start with what everybody knows. What's the circumference of a circle? Circumference of a circle equals 2 pi r. Well, what if we don't want the entire circumference? What if we just want half of it, or we just want a piece of it, right? You divide it in half. So the point of this is we're going to use radians. It's not 360 degrees times r, it's 2 pi r. That's the neat thing about radians, is it relates lengths with the angle that you've rotated through. And if you have an equation for position, you can turn that equation for position into an equation for velocity. In the case where our radius is constant, so this is kind of the nicest scenario out here, then what we have changing with time, so s equals r theta, r is constant, so we just have to worry about how that angle is changing with time, and this turns into our angular velocity. So instead of linear velocity, meters per second, it's angular velocity, radians per second. So it's how many angles we have gone through in some time period t. And the symbol for that is omega. And if we want to go from radians per second to meters per second, all we have to do is put an r in front of it. So v is equal to r omega. Get that relationship into your mind real good. So here we have v equals r omega. The arc length is equal to r theta. And this is another way that you'll see it written. So if you're looking at time derivatives, one dot above the angle would be the first derivative with respect to time, and two dots would be acceleration. So here's our angular velocity, just how that angle is changing with time. And if we take the next derivative of that, that will be the tangential piece of the acceleration. This is just one of the pieces of acceleration. So there's normal and tangent pieces. There's how the magnitude of velocity is changing and also how the direction is changing. So the tangential piece of the acceleration, which is just the next derivative down, this describes how the magnitude of the velocity is changing. So if we go from like 30 miles an hour to 60 miles an hour, that's this piece of acceleration. But we're not just changing magnitude, we're also changing direction. So we're not shooting off in a straight line, our direction keeps getting changed as we go around the circle. So we'll go through that other normal piece of the tangential of the acceleration too. So tangential acceleration, that's looking at kind of the magnitude of how fast that angle is changing with time. Normal, tangent, let's go through this. Hopefully you've seen this stuff again in physics, but I know it might have been a while. So acceleration is change in velocity over change in time. We have seen this equation over and over and over again, but it did not have everything in it. Okay, this velocity has a magnitude and it has a direction. This little red unit vector here is telling us that the velocity has a direction which is tangent to the circle. So that's like saying v sub I or v sub j. It's just saying that this magnitude has a direction. And when we take this derivative, we're not just looking at how the magnitude changes, we're also looking at how the direction changes. So here we go. Let's split this apart. So if we've got two things that are changing, so we'll take derivative of the first times second, second times derivative of the first. So we're splitting this apart. And for one of these little guys, we're going to do this crazy chain rule. So d theta over d theta, ds over ds. And why we're doing this, and whoever thought of this first was amazing because it works out nice. Okay, so dv dt, this is the tangent piece of it that we got. This is just the r alpha. So v, r omega, acceleration, r alpha, that second derivative of the angle. The direction piece of it, and this is going to turn into our v squared over r. This is the new piece of it. So here's the derivation if you want to see that. So what this goes into, if you have s equals r theta, or circumference equals 2 pi r or something, but when you take d theta over ds, what does that turn into? There's our 1 over r, right? V squared over r, we have 1 over r. And what else do we have here? Change in position over change in time. Well, that's our velocity. So here's one velocity, here's another velocity. So we have v squared over r. So here's our v squared divided by r. And then the last piece of this is how the direction is changing. So if you think about how that direction is changing, rather than the ball or object flying off in a straight line, it keeps getting pulled towards the center. It's pulled toward the center. So the direction that this is changing in is the normal direction. Okay, so there's the two pieces of acceleration. We have a change in magnitude in the tangential direction, and we have the change in direction in the normal direction. So v squared over r, or v squared over rho, that's the nomenclature the book uses. And this dv dt, this is going to be the r alpha piece of it. Okay. Here's the next complication. If the radius is not constant, so we're not just going around in a circle anymore, maybe the radius gets larger with time or something. And in this case, it's not tangent to the curve. The curve is changing, and so we have to change the name that we're giving to our coordinate system once again. We'll call this the radial direction. Draw something 90 degrees to the radial direction, and then we're just going to call that the transverse direction. So instead of x and y, we have some new names for calling things, and it's just one more thing to get rid of. Just remember radius, radial. So that's not too bad. Okay, so here we are. If we have the radius is changing with time, that little dot is changing with time, and we have the angle changing with time. So now we have two pieces to our velocity. If we go through, acceleration is dv dt, and now we have to take the derivative of each of these pieces, and it's a long derivation. I'll show you on the next slide, but essentially it maps out to this. So if both of the radius and the angle are changing, there are four parts of your acceleration you have to worry about. So here we have what's happening in the radial direction. So radial think of like x double dot or y double dot. That's the acceleration that's happening along the radius. And then r omega squared. This is the same as v squared over r. So this was the normal component that we had before is still there. So this is in the radial direction, or the normal direction, what we called it before, r omega squared. And then over here, this is what we had before, r alpha. Okay, so this is how the magnitude is changed. See, this is before we had constant radius. So everything with a constant radius, that's what we had before. The new piece of it is these little chunks where the radius is changing. Okay, so this is new, acceleration in the radial direction, and then there's also this 2 velocity times omega. So this is the velocity happening in the radial direction and the radial velocity. And to get through these, I'll show you the derivation for this, but you basically have to walk through each chunk of this equation. So if you have an equation telling you what the radius is, so radius equals 5t plus 3, then you can take the derivative again, and you have entire equations that you are plugging in for every term in this equation. So you just walk from the left to the right and you figure out what our radial acceleration is, what our radius is, what omega is, our angular velocity. So just walk through each of these terms and figure out what each one is. It's a lot to keep track of, but this is as bad as it gets. We're to the end of chapter 11. It's almost to the end. This is here's the derivation. I don't think I'm going to walk through. I'll just leave this up here so you can pause the video and study it out if you want to prove to yourself where this equation comes from. But it comes from taking the derivative of velocity, and now velocity has the radius changing, and there's a lot of stuff going on with velocity, and so there's even more things going on with acceleration. So you can walk through that derivation if you'd like to. Here's an example of something. Okay, so we have this arm, the arm is rotating around, and then there's a collar on the arm and it's sliding around. So the collar is not staying at a constant radius. But nice thing, they give us some equations. So if we have an equation for what the angle is doing with time, well, great. We can take derivatives, and now we have our angular velocity, angular acceleration. We have all of these little terms that we can plug in. They also give us an equation for what's happening in the radial direction. So r equals 0.9 minus 0.2. So we take this equation for the radial direction, and again, you can go through the velocity and the acceleration in the radial direction, and we'll take these and just start plugging them into this great big old acceleration equation. Now remember, this is a vector. So this is everything in the radial direction, okay? And this is everything in that kind of tangent, transverse direction. So don't just add these together, they're vectors. Keep everything in the radial direction, you just add everything here together and everything here, but from 1 to here, it's kind of an a squared plus b squared equals c squared sort of a deal. So figure out radial direction, transverse direction, and then remember these things are vectors. So at the very end, you're going to a squared plus b squared equals c squared sort of a deal. Okay, I think that was a long enough video. Study these guys out, but That is chapter 11. That was a long video, sorry. It's chapter 12 is so much shorter.